All right. Welcome everyone to week 4 of our fabulous online organic lab. This week we're going to be discussing and going over a simple and fractional distillation lab. It's a next typical part of purification of a compound. And if you were in the lab for the actual lab, what you would be doing is half of you would be doing a simple distillation and the other half would be doing something called a fractional distillation, which we'll of course go over. And then you'll be comparing your notes and seeing who got the most material quickest, stuff like that. But, we'll just talk about both of it for some simple discuss on this matter. So if you have your textbook, you would be going through section 5, and the pages of interest would be 43 through 69. There's going to be a decent amount of material covered in this lecture and for this lab, because not only is the chemistry and the process of distillation going to be discussed, but also all the unique glassware, the setup, and cleanup, because it's very important. The glassware is specifically made for these types of reactions, and there's a specific way to use it properly, and we need to go over that. All right, what is distillation? Pretty simple. I'm sure most of you have heard it before. Of course, most commonly distilled thing in human history has been alcohol, so that's probably where I'm sure most of you have heard of it. But in our previous lab, we talked about crystallization, which is a pretty simple, commonly used purification technique. The difference is crystallization can only be used for solid compounds because you need crystals, so you gotta have a solid. However, if you have a liquid at room temperature, you can't use crystallization, of course. So what we do in that case is we do distillation. Pretty simple. What distillation does is it separates liquids that have a mixture of different liquids in it, compounds, maybe even contaminants like we had in our recrystallization compound. But what this process does is it basically uses the difference in the boiling points or volatility of a compound. So volatility, you'll hear that a lot, especially in organic. That basically is just how much vapor the liquid in question is actually putting off at room temperature. And this has to do with a lot of things. By itself, it has to do with physical properties of the liquid, its boiling point, the pressure it's under, the atmospheric pressure. It can also form something called an azeotrope if there's different chemicals inside that can elevate or lower depending on what it has. But the main thing to remember is different compounds generally are going to boil off or have a different volatility than other compounds. Basically, everything is, for the most part, pretty, singular in what it does. So we're going to use that physical process and those physical capabilities of those chemicals to kind of separate things using heat. So, like I said, distillation is very commonly used. Tons of industries use it. Of course, anything having to do with alcohol, wines, beers, always used to distillation. That's how you take out the extra contaminants and water out of the alcohol, because anytime you distill alcohol, you're not just getting ethanol. As a matter of fact, the vast majority of what you're getting is water. The ethanol is there, but also anytime you use plant material, you're also going to produce methanol, which anytime ethanol has methanol, it's called denatured. And if you drink methanol, you go blind and can kill yourself. That's why the old-timey, hooch or moonshine, or the old homebrewed distilled stuff is dangerous because there's a higher percentage of methanol in there, and you drink enough, you go blind. So also there's a lot of, with the current COVID stuff, you might have heard a lot of stories about people distilling hand sanitizer to get the alcohol out of it, which is just such a crazy, convoluted thing to do, and it's just so much easier just buy alcohol. I mean, come on. But anyway, when you distill it out of something like that it's a part of that's not actually meant for consumption, they don't take the time to get the methanol out of it. So when you're distilling it, methanol and ethanol have a fairly similar volatility profile. So you're going to get a lot of methanol when you distill it out. So you're drinking basically almost 50% ethanol methanol. That's why you get a lot of people getting sick, poisonous. And the bad thing about methanol in a system is it's readily absorbed to the skin. Ethanol is as well, but methanol is very quickly absorbed to the skin. So you can actually get contact poisoning from methanol. So it's bad all around. But that's why they distill. You get the water out, get the methanol out, any other contaminants, and have a higher quality, higher percentage of alcohol. It's not just alcohol we use as distillation. Any type of refining for petroleum, cracked petroleum products, oil products, that's all distillation. There's a picture here of the actual Western Refining distillation terminal here in El Paso. And all those big steam pipes you see, those are distilling columns. Actually, they're just gigantic versions of the glassware you use in the lab if you were doing this today. They just have a bunch of different things, which we'll talk about, different plates, and they use fractional distilling. And based on how that works, the stuff that gets to the very top is your purest, and as you step down, you get different grades of petroleum products, and those are siphoned off by different systems, and they're all collected. So it's exactly what you would do in this lab, just on a massive industrial scale. No difference. Here we have a pretty simple setup for distillation. This is what you would commonly use for a simple distillation, a non-fractional distillation, which we'll cover next. So basically there's three main components. You have your boiling of the liquid mixture, which is taken part by a round bottom flask. You can see down the bottom left-hand side. The materials in blue, that's this part of the boiling liquid mixture. You have your round bottom flask, and we always use a round bottom flask because we want that curved surface area for your heating mantle to touch, so we get the most surface area that's in contact with the heating element. That allows a very even boil and less bumping and less bubbling of the material. And the heating mantle, of course, you put the round bottom flask into the heating mantle. We'll talk about the setup a little bit later, but that's your boiling section. The second section we've got there is basically a bunch of different components used to condense the vapor. The green section is a three-way adapter. It connects to the round bottom flask on the bottom. On the top, a thermometer, which is used to monitor and control the temperature to make sure you're in the correct boiling range for your specific compound you're looking for. And the offshoot tube that goes off to the right will connect to the condenser, which is actually going to condense the vapor into a liquid. The purple part is your actual condenser. This specific one shown here is called a West condenser. It's got a very narrow tube. It doesn't have any fractionizing in it. It's really simple. You have a water in and out valve, and you just basically run cool water through it from a tap. When your hot gas comes into that condenser, it hits the walls of the condenser. That cool water basically cools it down. It doesn't come in contact with it. There's a sheath around the inside, and that sheath is where the water runs. It never actually goes into the condensing tube. But it basically, the walls are cooled, so when the gas bumps to the walls, they're cooled, they collect together. When you get gas molecules collecting together and the temperature lowers, they can condense, and that's what happens. It condenses and very slowly pours out of the bottom. And that bottom will then go into a graduated cylinder or some other type of collection vessel where you can measure what you're collecting. And if you keep your temperature and everything stable and well done, you only get the specific molecule you want by controlling the boiling temperature. Pretty simple. So when it's fully set up and everything and connected, the section on the right in the red box is what it looks like. That's how it's set up. It's a pretty simple section. Nothing too difficult to worry about it. Just 3 or 4 parts, and you set it up and you go. You just watch it, control the temperature, and when it's done, it's done. Real simple. So how does this distillation work? Well, once you have everything hooked up, basically, like I said, we're going to control the temperature to separate a mixture of liquids that have a different enough boiling point. Now the key here is this distillation, simple distillation, really only works best when you've got about 25 degrees of centigrade of difference between your boiling points of your mixture. Like if we example what you would be doing in this lab, in the actual lab, would be you'd be using mixtures of methanol and water. Because water boils at 100 degrees Celsius. Methanol is 65, so that's plenty of a range where it can be very easily separated. And the reason you want that big of a difference is because even though, for instance, water boils at 100, once you start getting around 75 or 80 degrees, you actually start getting some water to boil off. That's basically due to, ions in the water, contaminants, stuff like that, that will lower the boiling point of water. So the more pure part of that water, that's just pure hydrogen monoxide molecules, will break apart and start to evaporate earlier. So you want that range so you don't get a lot of contaminants in your boiling. So That's the key point, is simple distillation. You want at least 25-degree difference between the boiling points. So if we're going to use this example of methanol and water, we'll just go through and quickly talk about how it works. So you would pour your mixture into that round bottom flask. Of course, before everything's set up, you don't want to be pouring stuff while it's all set up and heating. But once you got it all set up and connected, you turn the heating mantle up gently. Generally, you turn it up to about 50% on the heating mantle, the knob there, because you don't want to flash boil it. You don't want to, because if you start flash boiling it, you might boil off some water as well as the methanol. So you want a slow increase up to around 65 degrees. Once you start seeing 65-degree temperature, which of course the thermometer will read, what it's actually reading is the temperature of the vapor, not of the liquid. So liquid can actually be quite a bit hotter, which is another reason why this doesn't work well unless you've got a fairly decent range of differences in boiling point. But once that vapor gets to 65, you got to make sure that it doesn't get really over 65. You want to keep it right at that temperature, because like I said, you start going higher, the liquid's actually hotter, you start getting some water out and you get an impure product. That's also why you do it really slowly. You don't just crank it up right at the beginning. So once this vapor starts to come up, some of it's going up, but it's blocked from exiting by the thermometer. That's where the temperature is read. The other part of the vapor is going down the green part of the offshoot of the three-way adapter into the condenser. And because it's still only 65, because you're being careful and keeping it that way, that's mainly just going to be methanol vapor. So as it goes down that tube, it hits that cool condenser, it immediately hits the walls of it, starts to condense into liquid methanol, which then will drop out into your reaction vessel, into your graduated cylinder. So basically what you're going to do when you do any of this is you just keep it at that temperature until you stop seeing drops coming out. You're still going to have liquid on the bottom because you got water in your mixture, depending on how much, whatever's in there. But if you continue to heat it farther, then the water will start to come out and contaminate the system. So it's a slow process. To be honest, when you're in your lab, it's kind of annoying because you got to watch it and, every couple of seconds tweak it up and down a little bit here and there. But that's the point of purification. You want the purest products you can get. So that's how it works. So as it's all collected, you would first keep it at 65 until it's fully collected and you don't see any more liquid dropping out of that condenser. Then you would take that graduated cylinder away and label it as your pure methanol. And then you can do distillation again if you wanted to get all that water out of it. Crank the heat up a little bit, get it up to 100 degrees, and then when everything's out, it would just be all water. The key here is when you're heating these, you never want to heat anything to dryness, because that's a big temperature shock to the glassware. Even though these glasswares are rated at pretty high temperatures, if you do a temperature shock with nothing to transfer the temperature to, that glass can break. And the worst thing to happen is broken glass in a setup like a distillation setup. It's horrible, it's terrible to clean, you get glass everywhere, and the stuff's expensive, so you never want to do that. But that's just a simple basic of how a simple distillation works. And next we're going to talk about fractional distillation. Now we're going to go over a fractional distillation setup in comparison to the simple we just talked about. So if you notice on the bottom left, it's pretty much the same setup. You've got your boiling section, which is the round bottom flask, and the heating mantle. You have your three-way adapter still. You have your West condenser. You've got your thermometer and your collection measuring cylinder. The difference here is now you have something called a fractionating column. That's the blue part, the lighter blue section. Now, fractionating columns are used to separate mixtures into different fractions. And basically the way it works is you just have more time for something to be boiling. It boils, condenses before it even hits the actual true condenser. And this gives you a pure product, and it allows the impurities to settle back down lower in the column and to be refluxed and boiled again and vaporized. And that's basically all those little ridges you see, those are just fractions. And the bigger your fractionating column is, the more precise you can get. That's why the industrial ones, when money is involved, are huge, because the bigger it is, the more plates you can have in it and the more precise you can be. There can literally be millimeters of difference between one column and the other that will separate one product versus another, just based on the material the column is made of, how long things are boiling, the temperature you keep it at. There's a whole bunch of science that goes into fractionating and using a column, but it's a very common separation and purification technique in organic chemistry. So after you set them all up, it looks basically the same. It's just got that big extra fractionating column. Um, for what we do in the actual physical lab here, generally we have condensers that are very similar to West condensers, but if you notice, that outer sheath on the little diagram we have here is much bigger. You generally, if you run water through it, which most of the time when we're doing fractionating we don't, but if you run water through fractionating columns, you can put a lot more into it to allow cooler water coming in at the top, or cooler coming at the bottom. Depending, you can manipulate it on how you want. And the more ridges you have, the more fractions you have, like I said, the more precise it can be. But for us, we just use a wider mouth condenser, like a West condenser. It's called a fractionating condenser. And inside of that, we put basically copper mesh. It's specific, low grade copper wire that we put down there that serves as a way to force condensation without cooling the vapor, because just your gases are going to hit that copper mesh you have in there, and they're just going to naturally condense. But then you've got hot vapor still coming up, which will start to reboil it, and you get more and more precise steps as you go up. So the higher up the column, just like in an industrial thing, the higher up the column, the more pure the product you're looking for. So it's really like circled down there in the very bottom center. The really only extra item is that fractionating column. So it's set up the exact same way. You're just adding one extra piece in there. That's really the only difference. And it's run the same way too. You're taking the temperature of that vapor at the neck of that three-way adapter. You're just keeping it the same. You're collecting the specific fraction you want, and that's it. Why would you use fractional distillation versus simple? Well, the main reason is, like I told you earlier, for simple distillation, you want about a 25-degree temperature difference. Well, fractional can go a lot smaller. You can go basically down to 15, maybe a little bit less, depending on the size of your column. In terms of what we do in our lab, 15 is a good difference. If you need something more precise than that, you either need a more intricate setup with multiple outlets and might even have stacked columns, multiple different columns, or columns that have coatings that are tailored towards specific gases. There's a whole bunch of stuff you can do, but as everything in life is, the more precise you want something, the more pure you want something, the more expensive it is. So, of course, we're not going to let you work with anything expensive in the lab at UTEP, so it's just the simple basic stuff. So when you do fractional distillation, that vapor passes through that column before it gets to the West condenser. So this column allows that gas to kind of cool, because we're not running water through that fractionated column. It's just air cooled, and it hitting those little copper meshes allows it to recondense and then get heated back up by the vapor that's coming up. So basically what it's doing is all these little obstacles or ridges or column fractions, the little plates, allow that condensed liquid to re-evaporate, boil off again. And every single time this repetitive condensation vaporization cycle, every single time this happens, it's a more pure solution that goes up, gas that goes up than before. And this basically follows something that you learned in general chemistry. Hopefully you learned it. I'm sure no one remembers it, so I'm going to leave that up to you to look up, because I'm sure you're going to be asked about it on the quizzes. It's called Raoult's Law, and this condensation, fractional condensation, follows it precisely, 100%. So pretty simple way to understand it. So here at the bottom, we got a little diagram that shows what's kind of happening in a fractionated column. So we're going to use a solution of methanol and ethanol, basically a 50-50 mixture. So as you start to boil this off, if you're not really paying too much attention to the temperature, at the very bottom of the column, your vapor is mainly going to be 50-50 ethanol and methanol, because they have a pretty similar boiling point. Methanol is around 65, ethanol is around 72 to 74, in that range. So they're pretty close. They're far too close to do for normal simple distillation. You would have to use a fairly large fractional column. So as it's low, it's 50-50. The further you go up, basically, the lighter the gas, the higher it's going to travel. So methanol is a smaller molecule than ethanol, so you would expect the methanol vapor to be able to climb a little bit higher. Because as it's going up this column, you see those little blue ridges there. They're basically obstacles. All of those molecules are hitting those obstacles. They're going to hit them, they're going to condense into liquid, and they're going to drop back down. So the higher you go up, the more methanol you have in comparison to ethanol. Because the methanol is smaller, it travels faster, it can make its way up quicker. And then if it does condense, it's getting reheated by the vapor that's coming up. but your ethanol is heavier. It doesn't boil off at as low of a temperature, so it's able to drop back down, whereas the methanol keeps going up. So if you notice as you go up, it goes 50-50 at the bottom, then it can go up 60-40 on the medium, and at the very top, if you have your column set up perfectly for what you're doing, it should just be 100% methanol and no ethanol. This is what allows you to get a smaller difference in that boiling point difference between the compounds in your flask. So like I said, each condensation cycle in this fractional column yields pure and pure mixture, because you get what you want keeps going up, what you don't want keeps condensing and dropping down further, and never makes it fully up the column, because as this heated gas continues to rise, it's cooling. So whereas at the bottom, it might be that vapor might be hot enough to reboil your ethanol, about halfway up it starts being too cool. So you get less and less until the very top, where it's only cool enough to allow the lower boiling point to continue off. And that's the basic principle of fractional distillation. Okay, now we're on to our actual laboratory procedure as it would be done if you were in the actual lab. So the first part we're going to talk about is the simple distillation, which half of you would be doing. And this is how you would set everything up and get it going. So the big important part is anytime you're working with glassware, especially connecting pieces of glassware, you have to use a silicone-based grease around the joints. If you don't do this, the joints might slide together and fit nice and well and even be tight enough where they don't slide off. But as hopefully most of you know, if you heat or cool glass, it contracts. So when you're heating it, it expands. When you cool it, it contracts. That's the way it works. So as you're heating this is going to expand. And if you don't have that thing greased, you can get heat shock, and these glass molecules will actually lock together permanently, or they can shatter. Now, silicone grease basically allows them to slide. They can still stay connected and, for the most part, fully joined together. You can use clamps to hold it together, but it allows it not to become heat shocked and be heat stuck. It's very important, because once it's heat stuck, it's basically impossible to get them apart without breaking them, and you just lose them. So the number one most important thing, and I'm sure this will be on your quiz, is anytime you're connecting glassware, you always use a silicone grease, unless stated otherwise. Sometimes some of the volatile solvents we use, for instance, dichloromethane is one big one, that can actually dissolve the grease, and then you have contaminants in your material. So specific things will tell you not to use it, but 99% of the time you're going to use a silicone grease on all your glassware. So what you're going to do is you're going to fit the round bottom flask, your three-way adapter, your thermometer adapter, which is basically just something that caps the three-way adapter that the thermometer can slide through, so it's not banging up against glass. It's just a little rubber stopper with a hole in it. And you're going to connect them together nice and tight, and then you're going to clamp the round bottom flask to a iron stand. Basically just like 3-prong clamp, something like that, just to clamp it to make sure it's all nice and set up straight. You want to clamp as much stuff as you can get, because a lot of the stuff is top heavy, side heavy, and you don't want gravity or just to look like it's going to hold there, because like I said, there's silicone grease, so it might be holding there for a couple minutes, but it'll slowly start to slide off. So everything needs to be clamped. A lot of times we'll give you rubber bands, and you can put the rubber band around those water in and out outlets on that west condenser, and then put the other end around the other side of the three-way adapter, and that keeps it more than safe, because those things aren't going to get hot enough to melt the rubber band, so they're perfectly fine to do that. But sometimes you don't need them, sometimes you do. It just depends on what your TA wants you to do. But once that's all clamped up and set on an iron stand, then you're going to add, before you put the thermometer down in the adapter, you're going to add 10 milliliters of methanol, 10 milliliters of water, and 2 to 3 boiling chips into this round bottom flask. And so we've got a methanol water mixture, so 2 different compounds with more than 25-degree boiling points. And these boiling chips, if you haven't used them before, what they do is they provide extra surface area for nucleation sites for gas bubbles. And they basically make it easier to boil, number one, and number two, because instead of having your gas bubbles form all over the place, which leads to, like if you're cooking, if you're boiling water, the water pops and roils all over the place. If you've got that easy nucleation site from those boiling chips, all of your bubbles form at that point. So those bubbles are coming up in the exact same place basically every time. So it basically, one of the good things it does is it stops the popping or the boiling over when you're boiling something. So it's a more controlled boil. So you're going to put all that in your round bottom flask, and then you're going to put the heating element under it. Now the deal with heating elements, anytime you're doing any type of distillation or anything using them, you always need a ring clamp under the heating element. You don't have the heating element directly on your bench or on your fume hood table. The reason for this is if your reaction goes awry and the temperature gets too high and it starts to boil over, you need an incredibly quick way of getting the heat off. If you just turn it off, that heating element's still hot. It's like if you're cooking something on a stove. If you turn the element off, it's still hot. It's still going to be hot, and something's still going to boil for maybe up to another minute. So what we do is we put that ring clamp under the heating element, and you put it a few inches above the top of the bench or your fume hood. This allows, if something bad happens, you can just loosen that clamp and literally drop the heating element a couple inches away, and it'll really, really quickly stop the heat. So that's something that's very important, and that has to be done anytime you're using a heating element. You never put the heating element directly on the bench. Always have a clamp under it for safety. So once that's done, you just connect the power to it, and you turn the dial up to 50. Now for fractional distillation, the setup is basically exactly the same. You just have that extra added fractionating column in the middle. So when you get the fractionating column, it doesn't have the copper inside of it. So we would give you the copper, and you would slide it down the mouth from the top and pack it in there. You don't want it too tightly, because then the gas and the liquid will be stopped. It'd be like a stopper in a sink. You want it fairly loosely packed in there, but enough where it's got enough little ridges for the vapor to stop. It's kind of a trial and error type thing. You just got to get used to it. Same thing with everything else. You got to make sure you have the silicone grease on all the joints. Set everything up the same before you put the thermometer in. You put your methanol, you put your water in, you put your boiling points, make sure everything's connected up. Make sure the heating element is off of the surface. Same thing, ring clamp on the bottom of it, and everything's set up. Dial it up to 50. So both of these are set up the exact same way, except for the extra fractionating column. Once you get that heating mantle dialed to 50, all you're going to do at this point is just start watching the temperature. And on the next slide, we'll show what we're going to do with what we're collecting, how you're going to monitor this, and the proper way to keep your, basically your, we call it a vaporization ring, basically. You're going to look for a specific ring, and if that ring's in the right place, you know you're pretty much doing okay with your distillation. Okay, so now we've set everything up, we've turned the heat on, now we need to start carrying out the distillation. So both of this fractionation and simple distillation are going to be carried out the exact same way, because it's only that extra piece that matters. So once it's all set up, it's done the exact same way. Don't need to do anything different. So the first thing we need to do is make sure we have cool water circulating in that west condenser. And the important part is how the water comes in and how it comes out. So water is going to go in at the lower outlet valve, the one that's further down in terms of gravity, further down the chain, and it comes out of the top. Why is that? Well, think about it. If you have something that's slanted or even vertical in some cases, and you have water coming in at the top and coming in at the bottom, it's going to be rushed out by not only the force of water coming in, but gravity. So it's going to rush out, it's going to go out as quick as possible, so it's going to spend as little time as physically possible inside of your condenser. If you have it the other way, if you have water coming in at the bottom, slowly filling up and then exiting when it overfills at the top, that water is in the column much longer, allowing for a longer cooling process. That's the reason why water always comes into the bottom, out the top. Simple. That's the way it always works. So once you've got that set up, you turn the water on, and you want to slow it. It doesn't need to be gushing, just a nice slow trickle, so water is just moving. That's all it has to be doing, just constantly moving, constantly filling with cool water. That's what you need. Make sure that transformer is dialed to 50 for your heating element. And then at this point, you're just going to monitor that vapor. It's slowly going to start putting off vapor, and you can see it rising up the column, because as the vapor comes up the column, it's going to hit a point where it starts to condense. And at the beginning, its temperature is not going to be high enough, so it's going to start condensing in the column. Before it even hits that west column, it's going to start condensing sometimes in the round bottom flask. The longer you heat, it will start condensing inside of the three-way adapter. But what you're looking for basically is about halfway up the three-way adapter. You're going to start looking for a ring where you start seeing little water droplets or liquid droplets on that ring. As long as that little ring of condensation isn't above the arm that goes out to the West condenser, you're good. If it's above that, that means we might be getting some water vapor or some of your other liquids above that. The temperature is too high. Of course, you've got a thermometer in there so you can judge exactly the temperature that the vapor's in, so you don't need to judge it that well. But if you don't have a thermometer or you're just doing a quick setup, you use that vaporization ring as a good test. You don't want it up above the point where your vapor's going off to be cooled. You want it always below, because that allows the cooler things to condense and the hotter gas to go up. It's kind of like a manufactured fraction, a manufactured plate. But that's when if you see anything about a vaporization ring, that's what we're talking about, is the point at which stuff starts to naturally condense. That's what we're talking about. So as the vapor starts to rise, like I said, it starts to condense and follow down the three-way adapter into the West condenser, you're going to start noticing that it's definitely going to start condensing almost instantly as it goes into that West condenser and start rolling out as little drops of liquid. Now, make sure that the outlet is actually going to be dropping into a cylinder. There's a lot of adapters you can put on the end of that West condenser to channel it better, but most of the time, as long as the cylinder is wide enough, it can just drop straight in there. So as this starts to drop out and slowly distill out, you're going to get a few drops at a time. For a little bit, it might be fairly consistent drops, but it's not going to be a fast process. It's pretty slow. And like I said, we're only would be collecting 10 milliliters. It would just be the methanol that's boiling out of the water at this point. So we put 10 in, so we expect at least 10 out. So you would do this until you get around 9 milliliters, and then you're going to notice it's going to be dramatically slower. As long as you're keeping that temperature around 65 Celsius, it's going to be really, really slow to maybe even completely stopping. At this point, when you don't see any more liquid coming out, you can say, all right, I've boiled off as much as the methanol as possible. So then at that point, you would take that graduated cylinder away. You would mark to see how much you had. And then the rest of the stuff in the round bottom flask, you can pretty confidently say it's mainly just going to be the water. There might still be some ethanol in there, but it's going to be very, very little. The key point, of course, is not to boil it all the way to 100, not to make your flask dry. You always leave at least a milliliter of liquid behind, even if you know what you're distilling. In our case, if you were doing this in a lab or you didn't know what you were doing, you would be doing this by trial. You're not sure what you've got or at what point something starts to boil off. So you always leave at least a milliliter of liquid behind around the bottom flask. You never heat them to dry. That's the big important part. And I'm sure there's going to be a question about that.